Good afternoon, everyone, and welcome to the Formula Bharat Academy Workshop this season. We are glad you could all make it to this virtual event. Before we begin, kindly mute your microphones while present in this room. If you are stuck amongst others, hold on the letter G to move through a crowd. Please maintain the decorum of the room. As our speaker will be presenting via Zoom, you can view his presentation via the video thumbnail on the bottom right of your screen. Double-click the thumbnail for a full view. To submit questions during this live Q&A session, kindly locate the green board on the top or bottom of this room. Click on the letter X and fill out the form. Our speaker today is Dileep Prabhu of Robert Bosch Engineering and Business Solutions India. Dileep has around 11 years of experience in gasoline system calibration, modeling and simulation, and embedded systems. He started his career as a powertrain calibration engineer at Bosch and maneuvered his career in different domains from calibration, embedded software development, and system engineering CO2 reduction applications. He has played a key role in calibrating several projects of Indian OEMs. In his current role, Dileep is a team lead for AI and efficiency topics in calibration, which includes AI model development and simulation for improving calibration efficiency and training and development of automation methods at Robert Bosch. He's also responsible for the development of data analytics pipeline for fleet analytics at RBI. He graduated from PS University Bangalore in mechanical engineering and has recently done a micro masters in analytics from Georgia Tech through an online platform. Dileep is a continuous learner and has great fascination for new technologies and for solving real world problems. Without further ado, please welcome Dileep Prabhu. Dileep, you may go ahead.
Hello, thank you everyone for coming here, and thank you Getty for my introduction. So hope everyone can see and hear clearly.
Yes, you can see and hear you clearly.
Okay.
Yes, and we can see your screen
just
as
trying.
well.
Okay. So good morning everyone for coming here on Sunday and making some time and for going through all the different topics. And today I want to show about the specifically a method like we normally hear a lot, like AI, artificial intelligence, and machine learning, deep learning, and how it is going to help us in optimizing or calibration zones. It's mainly that I want to touch upon a topic that it is not just for artificial intelligence is not just for digital marketing or kind of face recognition and automated cars alone, but it is also useful for solving quite a lot of engineering problems, which are not normally explored by tech geeks. So today, we started an initiative of looking into how we can solve our conventional optimization problem and calibration problem using newer methods. So that was the effort that we started working on these ideas, like say quite some 2 years before. And now we reached a stage where we identified the problems and identified the areas in optimization and calibration problems, and then how do we solve with these methods. So maybe I'll skip the introduction part, is already discussed. And so let's go through a brief introduction, like agenda, what we talked today. And so that you know like what is coming up in next and what sequence the talk is structured on. So I want to just give a brief introduction about this EMS, but I'm not sure like everybody here are all the time or full time working on tuning area, or you might be working into the design objectives or the chassis and so on. But just thought of giving a very small brief introduction. Just let me take the laser pointer. Okay. And what is the objectives that we do typically, that what is our objective in calibration, and what is the motivation for choosing calibration, and also looking into what problems that we can solve. So we want to look into a very big motivation. And then going further, we want to discuss, I would like to give an example of, there are two techniques that is widely used in solving the cal problems. And there are two things called steady state and dynamics. So this name looks a bit complex, but so when we go in detail what exactly the problem that we're going to solve here, so you will get an idea that, okay, so some of things you might already be doing. in a different way, but how it could be solved in an AI or the machine learning methods. And also, I would like to give a detailed example of one project which we started last year, and which was basically optimizing emission problem. Means that using a data-based approach, simulating the engine out emissions, because as we know, the emissions is a really big problem, and that is like government is enforcing the newer norms, and that is a major problem that we are today dealing with, yeah, in order to reduce the emissions and so on. So how is an AI method would help us to model such an problem, and how do we use it to ensure the robustness of calibration? And again, the challenges. So because it's like, yeah, like we mentioned that when we go through all the slides, we know that the method is called data-based modeling, and it's really nice and powerful. It can solve and model really complex systems, but there are challenges, of course. And what are those challenges in these methods? And what are the current methods and future trends? Yeah, so today a lot of organizations have achieved really good breakthrough in using deep learning models and for a lot of areas like say self-driving cars and image recognition and so on. But in engineering problems also, we do have quite a good number of tools for solving the optimization problem very fast. And we also look into what are the future trends that we are going through. And the last one I want to say is that today we have a working prototype called full vehicle simulation, which is being done in Germany, and it's also been used in proposed to other OEMs also. And we will see how that problem is being done, or how the entire simulation is being done. So as you see, this is a typical layout of engine management system. Maybe you would have seen in many books and training materials, especially this is the kind of typical diagram that we have it in Bosch to explain the EMS architecture, and also to explain what kind of sensors and actuators are typically used and so on. So if you see the engine block, there are lots of sensors and actuators that we use, and overall using all of them is to meet an objective of having a better drivability, better performance, and better fuel economy and lower emissions. So there's always a trade-off between, making a car drive really smooth and like a very aggressive way and very smooth way. And also there is looking into another objective of meeting the emissions even in all the drive modes possible. So maybe we will look into the next slide where there is always a optimization problem, or just a second. Yeah. So here, what you see here is, so there are two main objectives of any tuning that we do, or like we call this, like call it calibration of a new engine. So there will be two objectives. One is called legal requirement. One would be a performance and comfort. So the normally legal requirement would be enforced by a government authority like ARIA and so on. And mostly that we have to satisfy these points in order to sell our vehicle. Okay, so which will be like, yeah, emission test, and yeah, so idle test in fields, and OBD requirements like onboard diagnosis, where it should be able to self-diagnose its catalyst after and exhaust after treatment, and also has to ensure that the vehicle is able to, deliver the lesser emissions for a specified duration of kilometers and so on, like say 150,000 kilometers. So till that car should be able to self-diagnose itself, and if there is any issue in terms of emission, it should throw a mill lamp and the other legal requirements like evaporative emissions and so on. And other part of the trade-off is performance and comfort. Okay, so as you know that there are some cars which are like very good drivability, very good performance, but it's always take a toll on reduced fuel economy. So if you see the graph on the right, so the best fuel economy point, that means like, yeah, if you're trying to get more out of the gasoline that we consume, it is not always you get a very comfort, like very good drivability, because yeah, it cannot be very aggressive. And in terms of emission, if you see the blue line over here, so the point where the emissions are lowest, not necessarily has to be the very good or optimal point in terms of fuel economy and yeah, the driving pleasure, of course. So there is always a trade-off between these two. The dotted lines, if you see, if you are trying to optimize the fuel economy, then you will have a compromise on the emissions or the power delivered. Like it cannot be very aggressive, and it's very fun to drive. And if you make more fun to drive, kind of tuning, so your emissions going to be bad, and at the same time your fuel economy going to be lesser. Okay, so here there is a challenge is that you need to have kind of trade-off between these two, between all three as a my primary objective, and still achieve a best point, which is yeah, satisfying all the conditions. So in this kind of scenario, just a second. So this is one typical example of emission test. Yeah, just want to show what is the complexity in emission test, and also like what is the trend that is happening right now, which where we are moving towards the testing on the lab from testing on the road and more real driving conditions. Yeah, so this is a typical example where the vehicle will be mounted on a chassis dyno, and the pollutants gases will be measured at every second, and the vehicle will be driven on a test cycle for around 20 minutes. And the cycle that you know, like MIDC, we call it modified Indian driving cycle. And this is an NEDC cycle, but yeah, in India, what we have is a MIDC cycle. That means the each and every vehicle that we release on road has to be undergo this test, and there is also a limit specified by the government that the total emissions accumulated by end of this cycle should not exceed a certain value. All right. And there are three different pollutants which are normally harmful, which are the byproducts of combustion. And these are all mentioned by authorities that, yeah, this should be the limits in terms of this. They mention like they mean the milligram per kilometer and so on. So this is one of the main objective or a challenging that we have after we tune the engine tuning and drivability and so on. Then the last activity is the emission optimizations, right? So after we tune everything like chassis, mostly be done by OEM, and we take care of emission calibration, like overall engine performance and tuning calibration. After a drivability cal, and we come to emission, and we see a lot of increase in emission values due to aggressiveness by either by driver, either by the pedal maps, or by the way the drivability is, or even by a lot of different factors. So it is always back and forth activity that we go to the road and we retune it, and then we come back to the lab, see if it is working properly. Okay, so this is a lot of time consuming, iterative, and also the subjective field that we have in reliability. Team will also have to be compromised on this, but at the same time that we have to meet emissions. So yeah, there are a lot of iteration that happens back and forth, but this is the trend till today. That is like BS6 emission norms. So going further, what is happening is like you might also heard from Europe and US that the term called real drive emissions, which is being coming and in BS6.2, as they call it stage 2. So in the previous slide, which you saw about that the method so far today is that the emission values will be measured from the vehicle on a test cell, which is like closed environment and like simulated something similar to a road condition. But that is not enough, yeah, because of traffic conditions and driver variations and a lot of other factors. The test which we do it on the steady state was not really close. So then that's where the trend we have is moving towards on-road condition. That means the whole emission lab facility is running just behind the car, connected to the exhaust, and where we will be able to tell whether the car is polluting more, or is it under the legal limits and so on. And there are like different conditions also put. This is from again the legal authority that the vehicle has to be driven in the equal share in urban, rural, motorway, and so on. So the way I'm talking about this is creating a lot of challenge in terms of tuning the vehicle in satisfying all the requirements like from fuel economy, better drivability, and emissions. So this is costing a lot, and the whole equipment costs even more than 2 crores, a single equipment, and it's not really easy to swap between the vehicles. Like OEMs will have a number of variants and number of vehicles it has to be tested and so on. So in order to cater this problem, yeah, so what we looked into is the whole emission problem that we looked into is what is the problem today that we are facing, and how that could be done in differently in newer methods. So like we all we discussed before in the previous slides, I mentioned that yeah, that we are moving towards a very stringent emission norms like BS6 and RDE is coming, which is real drive emissions, and we also have like they're being enforcing on CAFE norms and so on. And there's also a robustness on the real driving cycle. Is there is a necessity because yeah, authority can test the vehicle anytime after it is being released, and they'll look if the values are still within the limits and so on. So we have to ensure that robustness is quite good. That not just for the OEM to get the certification from authority, but it's also for the vehicles to be running on the road should also be meeting with all the legal values. And like you mentioned, the facility cost is very high. Such a facility, like either it on a stationary or on the road, like we have mentioned here, that each emission test costs 1 lakh rupees per test. Yeah, and there will be like typically 50 tests in a typical project that takes in order to tune for meeting the legal values. And there is also high load. Like as you see, the number of vehicles being released last year is quite high in terms of number of variants. A lot of different OEMs are coming in because it's untapped market, and the small segment vehicles is booming here in India. And there's so much of variants and yeah, vehicle demand that is coming for, especially for tuning, and the increased project and complexity, because as we know that the overall objective is that every time a OEM comes up with a new design on engine, they always try to squeeze, like objective is to how to squeeze more by consuming less, kind of lowest BSFC and so on. So for that, there are different engine variations or techniques is being used on a traditional combustion engine. So all of this is creating an insane complexity, time, facility cost, and all these things. So then what we did is we were exploring the method called machine learning based optimization. So here there are two techniques. So the traditionally what we've been doing on engine dyno is that we mount the engine on an engine dyno and then measure each and every operating points, and then we tune the points manually in order to get the required output. But today the manual approach is not possible because, like we mentioned, different variations and variability on the engine components. So approach what we used is called a data-based modeling. That means the measurement data will be selected in such a way in different operating points, and also the inputs are chosen such a way that the model can learn the behavior between the inputs and the outputs, and it represents like an actual engine. And later, this model, which is we called a database model, would be used for optimization outside the engine dyno. So such an approach is called data-based modeling. So this is one example that what we are trying and what we did. And there is also advantages like it is possible to simulate the entire engine operation without having a necessity of having engine dyno or a vehicle simulation. Okay, and there are also different use cases that it is really easy to get an optimized maps which satisfies the lowest PSFC and better stability, better combustion, and so on, just by having very few optimization points without actually manually doing it on a dyno to make sure that all the points are satisfied. Okay, so maybe we will go on another example here. This is we are talking about what we are calling as a steady state engine dyno calibration. So that means the engine will be mounted on engine dyno, and like we mentioned, the target is to optimize the points which are the lowest consumption. At the same time, the pollutant values that comes from engine will also be lower, and like noise, stability, exhaust temperature, and so on. The primary objective would be having like reduced CO2 and also reduced emission values. Okay, but there are different operating points at which an engine can run. I mean, operating points, I meant that an engine can run from 1000 RPM to 6000 RPM typically. And but there are different strategies at which it could be tuned. What is the ignition angle that you want to optimize? What is the VVT, variable wall timing you want to select, and so on. So if you see here as an input, like we have a speed, load is the main, the range at which it should run. And there are different parameters that to be optimized, like injection timing, ignition time, fuel pressure. This is in case of GDI or diesel engine. EGR again, camshafts, intake, exhaust camshaft, intake camshaft. So what does it mean? Like having all these input variations mean is to achieve the target, which are like, yeah, like you mentioned, the lowest PSFC and better emissions. But how do we do? Because when we try to spread out all the variations on a paper, like in factorial map, This is going to be nearly 30 to 35,000 measurement points in order to see which is the best by having all the combinations. Okay, but that is really a huge point, and each points means like measuring each point on an engine dyno in a steady state condition would be say around like 3 minutes per point, and like 30 to 5,000 points will take more than 2 3 weeks of time. Yeah, so this is quite huge. So there is another method what we been doing for at least quite some years is called DOI based database modeling. So I'll try to touch that point here. So what we call is design of experiments here. That means instead of measuring each and every points possible on an engine dyno, we select the points which are boundary. For sure, we say what is the boundary at which we have to measure the points like lowest engine speed, highest torque, and highest mass flow, and so on. And there are different techniques how we generate this DOE. There are tools available, but yeah, one of them like we are using is a tool from ETAS, which is ASMA. Yeah, and so that's what. But it could be done in a lot of different ways. And this approach is called full factorial approach, but not measuring all 30,000 points, but instead say around measuring only 1,000 points, which covers the entire operating range on the engine, and then use this data to model the behavior of the engine. That means using these DOE points alone, we're going to represent the working of an complete engine operation condition. And this is we can also consider that as a plant model or like engine model. But here there is no physical equations behind it. Yeah, so it's not that it's not like a GT suite model or some kind of one-dimensional model where we specify how many cylinders, what is the size of the each cylinders, and yeah, the power output, friction, and so on. But instead, this method is that we directly measure everything from engine, and then we model all the points to a model which could represent like an engine, which would be used further for optimizing the maps and curves inside the ECUs. Okay, so the next step you see, and I also want to touch here that the model that we used here is called the Gaussian regression. So this is one of the famous models in regression technique. Maybe in coming slides, we'll see which part of artificial intelligence that we are using here to make this model, and what are its significance, relevance, and yeah, like what is potential further like on solving the optimizations and so on. So having this model, which is built on a data, it's called data-based model, is quite very useful in terms of optimization. So that means the targets which we saw here, right? It is possible to define these targets in an optimization tool, saying that, look, I want to get the map values, or I want to identify what is the best injection time, best ignition time, which satisfies my lowest consumption and emission values. Yeah, so this is a typical optimization problem. And the modeling here, the model which we did is a function. Yeah, so it is like we call the function and we define the constraints that as these are all the function constraints which I want to solve, and this is the model. So that the output would be that we get directly the injection time values or ignition, injection, or EGR rate, and exhaust valves and intake valves position as an output directly. So this method saves quite a lot of time, and it's also very handy in terms of optimizing every time if you decide to change a target and so on. Okay, so earlier, if you consider, if you imagine that we don't have this technique, so you only have data which is captured probably in an Excel sheet or a CSV format from engine dyno. So one has to really go through each and every points to change or come up with the final value. And on a track, like if you see that something is really aggressive or if it is not meeting an emission values, maybe that is not the case for risk. But on a series, yeah, this is the normal, this is legally normally a problem where we might have to choose a different operating points, which is producing a lesser emissions and also producing lesser torque, because although like the operating point, which is very optimal in terms of torque, but it is not always optimal in terms of emissions. So yeah, there is some such kind of back and forth optimization happens. Instead of going back to the dyno or going back into the sheet and finding which is the other point, so this optimizer comes really handy and powerful in terms of generating the maps, all the maps at the same time. So this is one of the approach or technique. It's quite powerful, and it's very useful in terms of engine dyno calibration or optimizing, tuning the engine alone in steady state conditions. And yeah, this we call it a steady state. But there is also another problem. If you see that this only represents a steady state conditions, but if you see an actual drive condition in real drive scenario, only 30% of the time is you will be running in nearly steady state conditions, which we modeled here. But rest of like 60-70% of time it's always dynamic condition. That means it is transient. Yeah. So it's like one can imagine that the torque model, at least the torque produced by engine with respect to each change in speed and load and most of the time it is representable and is also directly proportional in terms of dynamics also. That means in steady state, if you measure an operating point which is producing like 50 newton meter, even in dynamic condition, it does produce 50 newton meter. But that is not always the case for the emissions and air filling and air fuel mixture in terms of emission and so on. There are quite different approaches we need to do than steady state in order to solve those problems. For that, so we have another technique called dynamic modeling, or is also called time-based modeling. So here the only major difference in this condition or the problem here is in the previous slide we saw the measurements are recorded in steady state condition. That means they are not dependent on time. Yeah, so it means like each and every point we measure, wait for some time for stabilization, we record them, and then we you pick those points and use it for modeling and optimization. But in real drive condition, what happens is the vehicle will be driven continuously where operating points are changing over time. So that means in real drive conditions that we have data which is incoming or which we record is always with respect to time. So we call that as a time-based optimization problem, or like time-dependent variables, right? So in case of time-dependent variables, it is not quite possible to model like how we did in the previous slides, which we saw a regression model would not work. So where we had to treat the entire measurement as in dynamic condition, and we need to learn the behavior of inputs and outputs, and we need to model them. Such an approach requires traditional example is if you want to make a plant model which is representing, which is helping in producing the output with respect to input, with respect to time, we need something called transfer function. Maybe those of you who are aware about simulation might have heard that in MATLAB Simulink, there's one such technique or method that we use to model a system. And normally what is used is called transfer function, or a system identification toolbox in order to identify what kind of system it is, and provided if you give an input and how would be the output, and how much time after how much time it realizes that output. But doing such a model using a mathematical way like MATLAB or GT suite calls for a very high number of parameters. We need to specify all the mechanical dimensions of engine, and some CFD will also come in, and we also need to know the coefficient of discharge, friction coefficients, and a lot of things which we do not know. Yeah, but all we have is just an engine where it is mounted on a vehicle, but I can drive, but I do not know theoretically. So in that case, so this is like machine learning or deep learning comes really handy, and such an approach we have is called database modeling, where we do not know anything about the system, but all we have is data, which can represent the about entire operating way. Like you had to record while we drive, and we had to capture all the inputs and output condition and bring back come back with all the data, and then choose what you want to model. So that is what we're going to look into it. So very first step in this approach is measurements. Yeah. So database model measurements or database modeling are always greedy in terms of number of measurements, unlike a physical model. So we have to have a huge amount of data. So how do we generate this huge amount of data? One approach is having a dynamic DOE, like in previous slide which we saw, which is called like static DOE. It's pretty easy to come up with a static DOE because you know what is the operating range of an engine, and then you can just equally distribute the points to be measured on engine dyno. But what do we do it on a vehicle? because it is continuously changing, and a driver A can drive very high aggressive rate, driver B can drive very smooth, and so it is quite a big space in terms of design of experiments. But yeah, there are different techniques available. One normal technique is to find out like what is the normal frequency of operating range and frequency of dynamic range, the dynamic conditions that at which driver drives. One would be aggressive, one would be normal, I mean mild, and one would be an urban driving pattern, one could be a rural, and so on. Yeah, so that is about the DOE. So once we have this DOE, once we identify how the measurement should be done. So the second important feature here is the feature identification itself. That means we have to identify what are the inputs that we need to capture and what should be the output of the model. Okay, so suppose in this example, like we were looking into how do I model my emission parameters in real driving conditions, means in dynamic conditions. So in emissions, if you see there are three pollutants, which is has to be normally optimized, which is THC, CO, and NOx. Out of these three, so we are just giving in as an example one, which is nitrox nitroxides that we have, and yeah, we have the different inputs like speed, load, lambda, ignition angle, and so on. So identifying these relations, like what are the inputs and outputs, is the second key step. Once we have enough number of measurements, and if you know what are the features which are inputs and outputs which my model is going to learn, and then the third step would be selecting a model or tuning a model. Okay, so in typical in AI application, there are lots of different models available. In the next slide, we will see where this model comes in, or like under a broad category, what is that this model that we are talking about. But maybe you can just think about this, that yeah, so for time varying condition or dynamic condition, there is one such models which are very proven and kind of state of the art algorithms which are developed by Google. One of them was TensorFlow, and all other things are wrapper around this library. So this guy is mostly been used for most of the image recognition problems and speech recognition problems, and even in Google search engine, if you type a word sentence completion, all of them has been done with this package called TensorFlow, and especially neural network, and there are lots of different variations in the neural network. So here what we are trying to look at is how this neural network can be used to model an engine application, especially like emission is one problem, but it not necessarily has to be this, but you can actually think of modeling anything, like say trying to model exhaust temperatures just by the thermocouple values and operating inputs. You would be able to model the exhaust temperatures very accurately up to 95% without using the sensor later. And one can actually think of having such model for representing the entire vehicle dynamics also. So there are like, the limitations is endless. There are like a lot of applications that we can think of. So once the model is done, so what is the next? Like, so yeah, there is a model which is running on my desk, which is going to predict or show what would be your emissions coming out of your vehicle for any input conditions. So as I mentioned that the typical algorithm which we use, there are two algorithms which are used for solving any of these 10 problems, especially on gasoline or combustion engine application. One of them is called recurrent neural network, and inside recurrent neural network, there is a sub classification or sub version of algorithm called LSTM. So it full forms long short-term memory, and this is from a TensorFlow package. And this is open source library, and one could think of using that for any problems from Python. It's pretty much easily deployable. And there's also other tool from ETAS where it handles all of them. Yeah, it's everything into a syncad package, which could be used for modeling and optimization and so on. And the next step, what we see here is optimization. Okay, so once we have this model, which is built from all the data. So when we say optimization, it's pretty easy that we just have to feed in the constraints that saying that optimization, hey, I want to find out what should be my ignition and what should be my lambda and so on. We can also relate it to lookup table inside the maps. Yeah, we can also say what dimensions of the values that we are looking for as an output. by giving the constraints or giving a target as I want to optimize or reduce this value lowest as possible inside based on any specific input measurements, or you can on the track measurement you want to optimize certain maps and curves. So then it is possible in this optimization block. All right, so maybe next we will slightly touch upon which category of artificial intelligence that we are talking about here. So if you see, I think the general term would be that people like we always see everywhere in advertisement. There is also something called general AI. So narrow or a weak AI is what we are today, which we are using for solving our problems. But general AI, which is much more advanced, that is, yeah, it's kind of consciousness as a kind of things like fully intelligent robot, which is interacting with us. So that is not what we are talking. And when we see an narrow AI or weak AI, there are another category that comes in called machine learning. And inside machine learning, there are different approaches. There are different methods called regression, classification, and so on. So the first example which we saw, which is solving the engine dyno problem or reducing the number of points on an engine dyno, which is actually using this algorithm on inside a technique called machine learning technique. Okay, so this is mostly used for steady state measurements, which are not time dependent measurements. If you want to model them with a very less number of points and for further usage of optimization, yeah. So then we just need to know thing called regression, and there are different versions, different algorithms available. So one of them that we use is Gaussian regression. And what about the time dependent variables? Like what if I don't have access to steady state dyno and I just have a vehicle on road and I want to capture those measurements and I still want to model like, yeah, steady state. So then we need to work on this time dependent variables where we have to go for a help of neural network. So which is a bit complex than machine learning. But yeah, there are algorithms which are specifically made for solving each applications. But inside that, like you mentioned in previous slide, so yeah, this is one of the state of the art proven algorithms which comes handy for solving any time dependent variable. Yeah. So this is also called like recurrent neural network. Inside this deep learning, we call this inside like artificial intelligence, machine learning, and the sub classification of machine learning is deep learning, where we are using neural networks for learning the weights for representing a plant. So this is about like an overview of like what part of AI is used and so on. So I would like to spend some time on the project which we did last year, and like what kind of approach that we took, what is the results that we achieved, and maybe that also helps you to think about looking into other applications or the problems which you solve and giving it a thought of can this be solved by data-based model. So here the objective was that so can we reduce the number of emission tests that we do using this data-based modeling? Like you mentioned in the beginning, the motivation that where typically we spend 50 to 60 emission tests for tuning and for a new project for achieving all the targets in emission targets. So this was the main problem statement, and the approach was that we decided that we wanted go ahead with the database modeling approach, where using like some AI methods, and we providing some identifying some input conditions and generating few measurements to model them. And the target is again the simulation of emissions for different cycles. So and how did we achieve is that we use the same technique as we discussed before, which is identifying good number of measurements. Like say we took some 10 to 15 emission measurements from engine dyno, and then identifying which are all the inputs and which are all the outputs. This is like feature selection is one of the main important thing. And the result what you see here, that we could achieve the emission values, like predicting emission values nearly to 90 to 95% of raw emission values. And we also tried for tailpipe emission, but it is very complex in terms of hydrocarbons and carbon monoxide, but the NOx emissions is quite good or quite achievable in terms of data-based approach. So this is one typical example, and maybe you can also see what did we model. So if you see the typical layout of engine, we get this oxygen value we get from oxygen sensor, and we also get the raw emission values That means that the pollutants coming directly outside after my combustion chamber, which are normally very high. The units which we talk like ppm, parts per million, and these gases will be passed through a catalytic converter, which after the chemical reaction, the emission that comes out of the catalytic converter would be way too lesser. And the integral of this is what the legal authority specifies. Over a test duration, the pollutant gases that comes outside the tailpipe or the end of the vehicle should not be certain value. So yeah, this is what we the layout what we had, and we identified the models which we want to do. So the very first model which we did was a lambda model, which means a database model is good, intelligent enough to tell what is the air fuel ratio or oxygen concentration at any given point of time. We can just specify what is the speed and load, and the model is going to tell what would be your combustion lambda. I mean the lambda in the exhaust. And there are subsequent models which are connected, and they are all done purely by data-based approaches. And they are connected in series such a way that if we provide a new measurements, and then we would be able to see what their emission values by end of the cycle or end of the measurement. So this was the example, and you can also see the results were quite good in terms of HC values. This is total hydrocarbon values, and this is the NOx value. Means the two things that you see, and the dark one is called the actual value. From the actual test measurement, and the light red one is from the simulation. You can see the simulation accuracy and the model accuracy is quite close, and it is following the same trend, except CO. But yeah, there were some differences here. And the plot what you see here is a typical the cycle data, which is like modified Indian driving cycle data for around 20 minutes. So around 1200 seconds. So yeah, you can see the blue and black, the two lines here. So which is this database model is mimicking or predicting the almost the same value as in real life conditions. So this is one of the results. And this is also about the algorithm. So if you are further interested, if you want to explore this database approach, you can just go ahead and Google this algorithm to know like how this method works. And there are also the open source library, like I mentioned. So one can just download directly from here, from the links, probably in Python, and one can try modeling them and see very good results. And of course, there are challenges in this approach. It's not that the database model is always easy than physical models. So I just want to touch the few challenges here. One of the main challenges is data availability. Like we discussed before, that this does not have any physical meaning for the algorithms, which doesn't understand anything. So data in, data out. So that means the garbage in, garbage out. So we need to have a really clean data in order to make any sense out of it. So what the thing is, the selection of data for modeling, like we need to, like if we already have enough number of good measurements, so identifying the good measurements which covers different boundary is always challenging. And again, the design of experiments. So it means, if you want to model an emissions of a particular combustion engine, so we need to create an experiment. That means it is covering in all the different zones, and also we need to measure all the data so that this data could be fed to model. So which is most of the time it is expensive. If you are generating measurements only for making a model sake, which cannot be directly used, or we won't be optimizing during while we acquire the measurements, but it would be used only for modeling it, but later it will be used for optimization. So generating data is quite a challenge. And another thing is feature identification. Suppose say you want to identify what are all the input parameters which influence my exhaust gases. All right, or even you can also think about like a torque, for instance. Like if you want to model a torque, what are the input conditions that you want to see? Because the torque could be influenced by fuel temperature, air temperature, density, what is the rate of opening of throttle, gradient, and so on. So identifying them is a bit critical. And The second thing is the modeling alone, because yeah, so model selection is quite challenging. But like you mentioned, but there are lots of good resource and tools available, and so people with over like yeah, so all these years of research, they identify what is the models which you to be used for solving some problems. So that part is quite already available. But there's also a problem called overfitting. That means this is a typical AI or machine learning problem where yeah, and so the model will be trained only for, or it works very well for the input data, but might not work very well for the data which has not seen during training. So that we call this as overfitting problem. And again, another thing called adding human experience and common sense. So in this kind of database models, like from our experience that we know, like for example, so engine is off, we know nothing should be coming out, but this model does not know. It thinks that it is some special state of input, and it still tries to produce some output. Yeah, so kind of like yeah, some basic things that we had to boundaries and constraints that we had to give. So this is a bit of a challenge, but yeah, at least the way the models are working is pretty good, and there are a lot of resources available to make it happen. And the last one is optimization. Especially this is a bit interesting, especially if you're trying to do with the time-based data, or not like an engine dyno data. That means that you drive few laps on the track, and you take the data and you model it, and you want to come up with an optimized maps. So then what happens is there is a chance of local optimization. That means the tuned data would work very well for the input it is given. Okay, so it might not work for different input conditions. So that is called local optimization problem. For that, we have to feed or we have to come up with a very good test cycle so that it covers all the different ranges of the operating conditions. So that is the optimal. That is one problem in optimization. Okay, so in the last 2 3 slides, I want to give you like what is the trend that we are moving into, and how is it going to be in future, like how is the optimization or like tuning industry is going to head in future, and what are the new skills it is worth learning, and so on. So if you see this slide, so this is the like, conventional or currently what we are doing today. That means we do a DOE and we take all the measurements, we model them, mostly a machine learning modeling we do, and then we use the tools to automatically generates the maps and cows data. We call this like optimization, and these values will be fed into this lookup tables inside the engine control unit and the ECU. So that means we are using the machine learning techniques only for calibration. Means it is assisting during calibration to come up with the best values, and these best values will be fed onto the lookup tables in the ECU, which is maps and cows. But there is also a trend which we are going through right now is what if we can directly upload these machine learning models onto the ECU where there is no optimization required, like where a calibration engineer does not need to say what is the best operating points at which engine should calculate certain things like ignition timing and injection angle. Instead, the whole machine learning model is running directly on the ECU. So ECU at any point of time can calculate the best operating points, best possible the points for the given input condition by itself. That means it does not need somebody who is tuning the engine has to tell like what is the best operating points. So the ECU itself is self-intelligent to know what is the best possible operating points at which it can run. So that is the next trends, or we already have some software for versions already available where with some test version is ongoing where these machine learning models are directly deployed on the ECU, and which is able to predict things by itself. And there are like a lot of different applications for this, mostly where it is complex, it is difficult to model using a physical model. So where this is a very good candidate for as an application where we can think of this. Currently some research is going on, and also some test is ongoing on virtual sensors. That means without using a sensor we are able to model them, and this model is sitting on the ECU to predict the output. So that means that we do not need this a sensor anymore. So we can just eliminate one of a sensor, and then ECU can identify the value by itself. And this is in terms of combustion, but in terms of electric vehicle also, there is a huge amount of work that is ongoing right now, basically on making this electric vehicle traction model. Maybe one reason is that because it is as an electrical system is quite linear and it is good, quite easy, and there's not much of parameters to be considered. So hence the machine learning model is very light and it is powerful. It's able to model the entire traction of electric vehicle. So which would be used for further strategy optimization and so on on board the issue. And we also have something called battery model. I think you might have heard that yeah, lithium ion battery is one of the complex and yeah, like difficult system. It's not very well understood in like how it deteriorates over time. There are multiple factors which influence it. So when we have this kind of complexity, when we cannot model it mathematically, yeah, so this kind of deep learning models are the best candidates, are very useful in terms of modeling a physical system. And such a system you can might have already heard called digital twin. That means the exact copy of a physical system is running somewhere in a virtual machine, and that would be used for prognostics, diagnostics, and so on. So that is the kind of trend that we are currently experiencing, and in future, like we mentioned, that yeah, this is the kind of approach that happens. And the last topic I want to cover here is that there's one big project that Bosch has started like working on for some few years, and now it's been ready, and testing is ongoing in Europe and other OEMs also outside Europe. So the project is basically identifying what is the robustness in terms of emission output when we drive the vehicle in different traffic conditions and different environmental conditions. All right. So like we mentioned in the beginning that we have an emission requirement. That means that we have to reduce or ensure that the pollutions are well within the limit on real drive conditions. That is RDE we mentioned. So there is a necessity that this vehicle has to be driven in all the different conditions with different driver, different route conditions, different traffic, altitude, and so on. So this is way too expensive and time consuming. And yeah, and the equipment itself does not support for measuring in all these conditions. So the approach what been tried by Bosch is that the entire engine, entire vehicle in terms of powertrain, chassis, and yeah, and like multi-ECUs communication, everything is virtually modeled, and the entire model is running on the computer. And where if we just provide the route information, like and the traffic information, like say vehicle A on a Google Maps or something, that you want to drive a vehicle from A to B on certain day in certain condition, and we would be able to tell what would be the emission values at the end of the trip, cumulative emission values, which are nearly to accurate as what we measure within inside the lab facility. So this is going to open a lot more opportunities for us for in terms of simulation, and also in order to ensure better tuning of maps and curves, so that yeah, the emission values are always lesser in all the kind of conditions and all the different in driving conditions so on. Today it is not possible because we don't drive in all of these conditions. Yeah, the legal authority says that you need to drive on a test cell and also some different cycles. But we do not know how a vehicle behaves in certain route conditions, certain altitude, and certain driver behavior. So now today, the amount of virtualization that we have is where the entire vehicle is possible to simulate, especially the combustion engine, so which is more complex in terms of the number of models which are connected in series. But in terms of EV, I think it's going to be it's not as complex as what we have in combustion engine. So there are going to be a lot of virtual and simulations that is going to happen. So yeah, it's like vehicle battery on cloud is one of the initiative, or one of the project what Bosch has, kind of digital twin applications. So yeah, so going further, what I want to conclude that is that not everything in future is going to be a physics-based model or one-dimensional model, what we have been traditionally doing. And we used to compromise with accuracy because we did not have enough data to model physical in a physical way. So in going further, what happens is going to be a model like hybrid models, we call this. So where 60 or 70% of the models would be done by a database model, which is like machine learning or deep learning model. and another 30% would be kind of boundaries or making some sense from experience would be done by a physical equation. So such a modeling technique would be called as hybrid model, and that you'll be going to experience and see in most of our conditions, like in most of our applications in future. So yeah, so I think that is all.
Great. Thank you, Dileep. We've got a question that came in quite a while ago. It was how
Okay.
do we use how do we apply AI or ML in terms of an EV powertrain? I would think it would be in
Yeah,
this
so
similar. Sorry, continue. Go ahead.
yeah, I think in terms of EV powertrain is exactly the same thing. At least in fact, it is more easy compared to an combustion engine. For instance, if you have an EV vehicle and if you want to model the energy consumption and so on, like we do not even have to have an engine dyno kind of environment like what we have on combustion engine. So where if we have an data logger, or I mean, we have a possibility to capture this high raster data on the electric vehicle, and if we drive with a couple of rounds on a track and so on, so it is quite easy to model a whole electric traction control using this database approach. But yeah, that like I mentioned as a challenge is that identifying how it should be recorded and what are these input parameters are the key challenges. For instance, like say one has to model a battery behavior. Okay, so we actually do not know what are the parameters which influence the battery deterioration. So now the research has been ongoing that there could be numerous factors like environment temperatures, ambient temperatures, which we normally not thought of, as we say that only what is there, the environment around the car is what we normally see, but there could be other parameters which is influencing them, so which we do not know. So yeah, like identifying those input features once we like feature identification and so on, and if you have enough measurements, so that is the most easiest or the best approach to model than going through a physical modeling approach like in like MATLAB SimSpace approach. So the data-based approach is always quite easy, and most of the time we see that the accuracy which we get in terms of the effort, like the time that is involved for modeling and time involved for generating measurements, is always easier in terms of database model in comparison to a mathematical model. But yeah, so only thing is that we had to have a good number of measurements. We need to know how our system behaves, and there we go. So then we can just model any parameters which we need, almost anything. But EV would be much like simpler than the problem or project that one that we've been doing, and we have quite good results too. Maybe we can also discuss sometime in the library or something if somebody wants to know what parts in EV is a good applications that we can solve from database model.
Great. Dilip, one more question I have for you before we move on to Roshan's presentation. If
Mhm.
a student wanted to go into this realm of learning about AI and machine learning, what would you
Mhm.
suggest to them in terms of programs, in terms of whatever material is out there? How can they begin?
Yeah, okay. So maybe I will share some links, but most of them are available in MOOCs platform. I mean, yeah, it's in open source platform. Like, we would recommend that there are a couple of very good courses which are not directly, it does not make anyone ready for programming, but as an understanding, theory is quite good, which is from Coursera platform. If you just go machine learning from Andro NG, I guess so. Maybe we can share some links which are the good training materials. But as a program environment, I would say Python would be more than enough to handle all of them. So one could reproduce and use the same results what we have from professional tools. All of them could be done from Python language itself.
Okay, great. Well, Dileep, it was great having you over here. To the participants in the Great Hall, you can meet Dileep at Hogwarts Library, and he'll be there to answer any other questions that you have during that short period of time that he's available with us. Dileep, thanks again for this presentation, and thank you to Bosch for sponsoring their time. And we will see you on Gather.Town. Charlotte will be there to help assist you and to get you to Hogwarts Library in case you need to
Yeah, okay, I'm
have
aware. Yeah.
that direction. Great.